Okay, good evening, everyone. So today we're going to discuss the FAQ that I shared in group regarding acid-base and also a short tutorial on acid-base balance. So menus will be overview on acid-base, then the differences between acid versus base and acidosis versus alkalosis. Then we'll delve into Henderson-Hasselbalch equation, and finally we'll discuss the FAQ that I've shared. Okay, my reference for these tutorials and for answering the questions that I gave is solely 90% from Carrie Brandis. So please go and read page to page 20, page 24 to 31 on Carrie Brandis. It is very simplified, very exam oriented, and answers are very detailed. Okay, please go and read that. After this class, we haven't done so. Okay, we go into the basics first. So what is acid, what is base? For this, there are multiple definitions given from Arrhenius, Bronsted-Lowry, and Lewis definition. Arrhenius said acid is a substance that increases the concentration of hydrogen ion in aqueous solution, while base is a substance that increases the concentration of hydroxide ions. Bronsted-Lowry definition is widely used in medicine, the one that we widely used in our practice as well, where acid is an hydrogen ion donor, okay, proton donor, whereas a base is a hydrogen ion acceptor, proton acceptor, okay. This is the Bronsted-Lowry is the concept that widely used in medicine. And Lewis definition is talking about electron. Acid is an electron pair acceptor, whereas base is an electron pair donor. This is just an opposite of Bronsted-Lowry. Here he's talking about proton, he's talking about electron. Okay, this is just for understanding. So bear in mind the one that we use mostly in medicine is all goes around Bronsted-Lowry definition. Arrhenius definition sometimes comes into play when we talk about dissolving a substance in an aqueous solution, where when you dissolve it, you see acid will produce a lot of H+, where base will produce a lot of hydroxyl ions. Okay. So acid-base balance. So what is meant by acid-base balance? Why is it so important for homeostasis in the body? So physiologic mechanism. It's a physiologic mechanism that keeps hydrogen ions of the body fluids in a range that is compatible with life. Hydrogen ions react with protein molecules of vital cellular catalytic enzyme. Okay, hydrogen ion, it reacts with the protein molecules which involve in vital catalytic enzymes. Such reactions change the physical contour of protein molecule, enzyme become inactive. Because if there is imbalance in the acid base, that we will change conformational change in the protein molecule that is involved in the vital metabolism, especially the enzymes. So that will cause the enzymes to be inactive. That's why the acid-base balance is important. To sustain life, must maintain pH of fluids within a narrow range, 7.35 to 7.45, corresponding to the hydrogen ion concentration of 45 to 35 nanomole per liter. Okay, this page is just an introduction. So acid-base balance is not an exam-oriented answer. Okay, so hydrogen ions form in the body. It comes from two types of acids. It's called volatile acids or non-volatile acids. Volatile acids mean acids that can be easily changed from one form to another, or acid that can be easily eliminated, whereas fixed non-volatile or metabolic acids are coming from metabolism. They are fixed. They are only can be eliminated in a certain way, and it's it's not easily convertible, okay, from one form to another form. Okay, a volatile acid is one that is in equilibrium with dissolved gas, okay, from a liquid to a gas form. And only volatile acid of physiologic significance in the body is the carbonic acid, H2CO3. This is the only volatile acid. As I mentioned, it can change form. Okay, carbon dioxide, is it an acid? No. If we follow, okay, we have Arrhenius definition, we have Bronsted-Lowry definition, we have a Lewis definition. In terms of Arrhenius and Bronsted-Lowry, carbon dioxide is not an acid. In terms of Lewis definition, it is an acid. So we'll come into that. Only volatile acid of physiologic significance in the body is a carbonic acid, which is formed by reaction with carbon dioxide and water, which is in equilibrium with dissolved carbon dioxide. See, this reaction can go forth and back until it reaches an equilibrium. So before we go further, I'll just go back to mention about the carbon dioxide. Okay, so this definition, you see, Arrhenius definition say carbon dioxide is something that can, acid is something that can give out hydrogen ion in aqueous solution. CO2 doesn't have hydrogen ion. So according to Arrhenius definition, it is not an acid. Bronsted-Lowry is a proton hydrogen ion donor. Again, it is not an acid. But in Lewis definition, acid is an electron pair acceptor, in which, yes. So there are questions. If you read Kerry Bendis, there is few questions regarding this. The CO2 is an acid. Is it a volatile acid? No. H2CO3 is a volatile acid, in which it is in equilibrium with the dissolved CO2. But by Lewis definition, CO2 can be considered acid. Because why we say this? In respiratory acidosis, we always say it is occurring because of high CO2. Actually, no. It is occurring because high CO2 reacting with water and producing bicarbonic acid, H2CO3. That is why it is indirectly considered as an acid. Okay, so just for the basic understanding of it. Again, you will see this equation a lot of time today. The questions I gave are all overlapping answers, so there will be a lot of overlapping discussion today. So this is the first part of the question that you must remember, you must know. This reaction is catalyzed by carbonic anhydrase enzyme, Ca, carbonic anhydrase enzyme. Okay, next. We talked about volatile versus non-volatile acids. So this is the equation that I told you. The volatile acid is H2CO3, which is formed by reaction between carbon dioxide and water. Non-volatile acids are produced from fixed acids or metabolism, metabolic acid like keto acid, ketone, lactic acid, organic acid like amino acids, and inorganic acids. They all will contribute to a fixed store of hydrogen ion, in which that hydrogen ion can be metabolized, can react with the body store of bicarb to also can produce this H2CO3, in which this H2CO3 can be broken down into CO2 and H2O, and the CO2 can be eliminated. Again, look at here. Sources of blood acids, volatile acids, again, water and dissolved CO2 producing H2CO3, which can be in equilibrium at this place and also at this way, where H plus is contributed by multiple other sources. It's just a repetition of here, we're looking in this. So the H plus that is contributed by the metabolism by the fixed acid can react with the body store of bicarb to produce H2CO3 as well. So these are two different types of blood acids. Okay. First we talk about volatile acid now, H2CO3. At this point, we are still doing tutorial. We haven't gone into the questions yet, but understanding this part will be easier to answer the questions later. Okay. Normal aerobic metabolism. Aerobic metabolism consumes oxygen and produces carbon dioxide. They produce very large amount of carbon dioxide per day. It means that carbon dioxide can react with H2O to produce H2CO3. That H2CO3 can broken down into bicarb and equal amount of hydrogen ion. Means more CO2, more hydrogen ion. So CO2 plus H2O. CO2 comes from aerobic metabolism, become H2CO3. H2CO3 broken down into bicarb and hydrogen ion. So as carbon dioxide diffuses into the blood at the tissue level, this reaction occurs primarily in the RBC, where it is catalyzed by carbonic anhydrase enzyme, an intracellular enzyme. It is an intracellular enzyme. Okay, I will come into why I'm emphasizing this. Most H plus produced in this fashion causes no change in pH. It's called isohydric buffering. Okay, it's called isohydric buffering because there is no change in pH. The buffer here is the hemoglobin. Okay, the bicarbonate reaction done by the carbonic anhydrase within the hemoglobin causes a isohydric buffering, which is they consume this H plus immediately and they catalyze this reaction to make there is no change in pH. A buffer is something that resists change in pH. Okay, so immediately buffers the H plus. The term is isohydric buffering. When blood reaches the lungs, the HB releases H plus to form CO2 as shown. Okay, here it picks up at the tissue level. Okay, then H2CO3 can be broken down into H plus. So again, this part, it comes here. Then once it reaches the lung, here the reaction goes this way. The CO2 from aerobic metabolism picked up, it goes this way. In lungs, it goes from here to here. The H plus that carried by the deoxyhemoglobin will release at the lungs. will convert bicarb become H2CO3. The H2CO3 will broken down to CO2 and H2O, and the CO2 will be eliminated. CO2 picked up at tissue and CO2 will be eliminated at the lung. Okay, this is the basics of how volatile acid being produced and also being eliminated from the body in terms of in the phase of carbon dioxide. It is formed from carbon dioxide and is eliminated as a carbon dioxide as well, keeping it in an equilibrium. Thus, there is no change in pH in a normal condition. Non-volatile acids or fixed or metabolic acid, it produced from the catabolism of proteins. Okay, so it is a fixed non-volatile acid such as sulfuric or phosphoric acid. Also, anaerobic metabolism also produce lactic acids, and we also have ketone bodies as well. Okay, so ketones also considered acids, keto acids. Okay, in contrast to carbonic acid, which is a volatile acid, can be easily eliminated. Non-volatile acids are not in equilibrium with the gaseous compound. This is the difference. Volatile means it is in equilibrium with the gaseous, whereas non-volatile are not equilibrium with gaseous compound. However, the hydrogen ion of fixed acid can be buffered by the bicarbonate ions converted to CO2 and water. This is what I mentioned here, the one that we talked about here, this part. This H plus can convert bicarb to produce H2CO3 and can be buffered via this pathway as well. Okay, so however, H plus of fixed acid converted to CO2 and water, the CO2 formed is eliminated in exhale gas. Okay, so fixed acid combined with the bicarb to produce H2CO3, carbonic acid, which can eliminated once it's broken down to carbon dioxide and water. Compared with daily carbon dioxide production, fixed acid production is small, only about 50 to 70 milli equivalent per day. Okay, that is the difference. Non-volatile fixed acid, certain diseases, we have increased fixed acid production. Here I've mentioned, compared with daily carbon dioxide production, fixed acid production is small. However, in certain pathological states, example in DKA, we have increased fixed acid production, or in a pathological state as hypoxia, increased lactic acid production. Here will be keto acid production. So hydrogen ions produced simulate respiratory centers in the brain, causes increase in ventilation to eliminate more CO2, pulling the hydration reaction to the left. So this is the part that we talked about. This is why patients who are hypoxia, when they're in anaerobic metabolism, they hyperventilate. Okay, because they want to eliminate the fixed store of H plus, which is coming from lactic acid. In terms of DKA, you see patient with DKA will come with increased respiratory rate. They will be having a shallow breathing, Kussmaul breathing and everything, because they're trying to eliminate as much of CO2 possible, which is produced from the keto acid, fixed acids. Okay. In this way, the respiratory system compensates for the fixed acid production, preventing a significant increase in hydrogen ion. Acid-base buffer system, as I mentioned, one buffer system is in the plasma, hemoglobin. Second buffer is respiratory system. Third buffer is the renal system. This buffer system in plasma goes on all the time. Respiratory system buffer is quite fast. Renal system buffer is quite slow but complete. Okay, we will discuss this in detail. Okay, buffer system mostly talking about only hydrogen ion. Respiratory system, H2CO3 and bicarb. Renal system is the one talking about everything else, including the fixed acids. Regulation of the pH by various organs. This is just a summary before we go into the depth of it. As I mentioned, in RBC and in blood, the system is the bicarbonate system catalyzed by carbonate anhydrase, where it stimulates your respiratory center, leading to hypoventilation or hyperventilation, depends it's acidosis or alkalosis. Or in terms of kidney either increases the secretion of hydrogen ion or it conserves more bicarb to bring back the acid-base balance. So what happens when there is acid-base imbalance? When there is acid-base imbalance, we develop acidosis or alkalosis. This is what happens in acid-base imbalance. So what is acidosis? What is alkalosis? You should be able to define this. This will be an opening question sometimes in Viva, or you can see in a SAQ or given also, it will be an opening question. The simple definition is Acidosis is a condition where blood has too much acid, resulting in a lower pH below 7.35. These are keywords. You have to mention it is blood has too much acid, or at least mention lower pH below 7.35. This is you must mention. You can start off with saying normal pH is 7.35 to 7.45, and acidosis is blood which has a lower pH below 7.35. It is divided into respiratory acidosis or metabolic acidosis. Why I add on this? Because the mark given is 1 mark. So just saying this lower pH below 7.35 might not get you the full 1 mark. So you have to say it is divided into respiratory acidosis where body retains too much CO2, or metabolic acidosis where body has too much acid or kidney fails to conserve bicarb or remove acid. This is just in case the 1 mark is broken down to 0.25, 0.5. Okay, but you can put it in very simplified point form. Same goes to alkalosis, is the other way around. Condition where the blood has too much base, resulting in higher pH more than 7.45. It is divided into respiratory alkalosis or metabolic alkalosis. Respiratory alkalosis, body expels too much CO2. It means it is eliminating too much CO2. Patient is hyperventilating. Metabolic alkalosis, either body is losing too much of acid or it is conserving too much, relatively increase in bicarb. Okay. So this is, I am not going into the compensatory mechanism in detail, or we're going to talk about ABG analysis today. So basically, you know this. Again, this equation you must know in detail. It is all about acid-base balance. You can see in respiratory acidosis, there will be increase in PaCO2. Okay, so CO2 high, the reaction will go this way and produce more H+. In respiratory alkalosis, there will be a less CO2, so the reaction will go this way and will be a less HCO H+. Okay, so that is why it becomes alkalosis. In metabolic acidosis, we have, because there is acidosis, metabolic acidosis produce a lot of H+, fixed acids H+. These fixed acids H+ will combine with bicarb to go reaction this way. So the bicarb being consumed to compensate for this H+. That's why there is low bicarb causing metabolic acidosis. In metabolic alkalosis, there will be a low fixed acid H+ production. So there will be increase in bicarb because the reaction will go this way now. So producing metabolic alkalosis. So must understand this concept as in simplified manner. Okay. Then we know about this compensation. What happens in respiratory acidosis? The renal bicarbonate retention. So PCO2 high, the body try to eliminate the increased PCO2 by hyperventilating, and compensation later on is bicarbonate retention. In respiratory alkalosis, the body is hyperventilating, so there is low PCO2, the bicarb will be reduced as well. This is what we see in ABG to get a normal pH. In metabolic acidosis, low bicarb, you have to reduce the PCO2. Means by hyperventilating. Metabolic alkalosis, high bicarb, you try to hypoventilate to increase the CO2. It's all about going back and forth in this reaction to maintain a isohydric buffering or maintain a neutral pH. How much is the compensation is successful, that decides whether we can get a neutral pH or not. Okay. So next, this is just to say again. So respiratory acidosis. Okay, in respiratory acidosis, as we say, there's increase in PCO2. The compensatory mechanism, kidney will retain increased amount of bicarb to increase pH. Respiratory alkalosis, low PCO2, kidney will excrete more bicarb. Metabolic acidosis, low bicarb, kidney will blow off CO2 to raise the pH, and this is the other way around. Okay, this is not, and I'm not going into this again. You will know this by now, and you know how much of the respiratory compensation or renal compensation as per change in millimeter mercury of PCO2 or milliequivalent liter of bicarb. This is just for additional knowledge I'm sharing here. Okay, we move on to Henderson-Hasselbalch equation, HH equation. A lot of you doesn't understand this. You must know this by heart. This is the base, the basic principle how acid-base balance works. If they ask you what is Henderson-Hasselbalch equation, you have to at least be able to write this formula. Okay, and then you have to say it is an equation that establishes the relationship between pH of acids in aqueous solution and their pKa, dissociation constant. the pH of the acids in aqueous solution, and their pKa, which is the acid dissociation constant. These are the words you must know. pKa is the acid dissociation constant. Okay, that is Anderson-Hasselbalch equation. I'm going to go in a bit detail about Anderson-Hasselbalch equation because what I found during my question to students or whatever, they don't even know what is Anderson-Hasselbalch. If they know also, they don't understand it fully. They don't understand the concept. They don't understand how it can be applied in a day-to-day practice as well. Okay. Again, I mentioned what is a pKa? It's an acid dissociation constant. We coming back to this equation. Ha, we just take it any acid. We no need to worry about CO2 here. Just think about any acid. Ha combined with water, it will give out a conjugate base and hydronium. The H from here combine here become H3O plus and releases a conjugate base. Okay. The equation, as we mentioned, the conjugate base over weak acid. pH equal to pKa plus log 10 to the upper part is conjugate base, which is the A minus, behind is the weak acid, which is the HA. Okay, so when we put it here again, pH is equal to pKa to the log to the conjugate base over weak acid. If you want to talk about weak base, you can just flip it, but today we're just going to focus on this. For understanding, you don't have to worry about this. Mostly questions are all asking about this part. So you just remember one. For base, it will be just the other way around. Instead of pH, we're going to write pOH. In our question and our day-to-day, we all talk about pH. So you just think about acid. No need to think about the weak base. So what you're going to remember is this. pH is equivalent to pKa plus log to the power of conjugate base divided by weak acid. Remember this, okay? You have to able to write this as the Anderson-Hasselbalch equation. The upper part will be the conjugate base, lower part will be weak acid. How do you get the conjugate base and weak acid? It's from this dissociation of a weak acid. Okay. So derivation, how do we come to this H&H equation? How do we actually arrive at this equation? How does it related to the pH? So for that, hydrogen ion of a buffer solution can be calculated if the concentration of the buffer's component and the acid equilibrium constants are known. It means if you know about the weak acid, the HA, the component is HA, water we know, and then if we know what is the dissociation constant, then we can find out about the hydrogen ion that is produced by that aqueous solution. Consider the bicarbonate buffer system. We are going back to the same equation, which is this. Okay, we're considering the bicarbonate, which is the most abundant buffer system in the body, actually, which is define the pH. So carbon dioxide plus water, carbonic acid, which is can be divided. So this is a back and forth reaction. It is catalyzed by carbonic anhydrase here and carbonic anhydrase here. Okay. The equilibrium constant Ka for H2CO3 is Ka equivalent to, we are not putting P here because we haven't log it yet. Okay, we haven't logarithmic yet. So that's why it's called Ka. So the Ka, the acid dissociation constant for this carbonic acid, for this bicarbonate buffer system is Ka equivalent to H plus times HCO3 minus divided by H2CO3. Okay, this is the equilibrium constant formula for any acid. Okay, for carbonic acid, H plus HCO3 minus divided by the H2CO3, it is the dissociation constant for this buffer system. We rearrange this, we will get H plus is equivalent to dissociation constant times with H2CO3 divided by bicarb. You rearrange that, you will get this because we want to calculate the H plus concentration, right? So that is why we rearrange that. Okay. pH is the logarithmic expression of the H plus. So you log this whole thing, you will get pH equivalent to pKa plus log 10 over conjugate base divided by weak acid. You all see how do we get this equation? This one, we get it by logarithmic logging this acid dissociation constant, initially change it to H plus, then we log it, then we get pH, log this become P here, and then we log here, you get P here, so pKa, log to the power of 10 H bicarb, which is the conjugate base, divided by the weak acid. So this is how we get this. So This is the derivation. How do we get it? So dissolved carbon dioxide is in equilibrium with and directly proportional to the blood H2CO3. This is what you meant. The CO2 is directly in equilibrium with this H2CO3 when it's dissolved in an aqueous solution or in blood. So H2CO3 is equivalent to KH times PSO. KH is your carbon dioxide is a gas which follows the Henry's law. If you don't know what is the Henry's law, please go and watch the videos that I mentioned about the gas law. And each gas has a Henry's solubility constant. And for carbon dioxide, the Henry's solubility constant is 0.03 mil per millimeter mercury. Okay, for the carbon dioxide. So since H2CO3, we don't know what is the concentration of H2CO3, but we can find out the partial pressure of carbon dioxide. So H2CO3 concentration is equivalent to solubility constant times the partial pressure of carbon dioxide. This is what we are talking about, Henry's law. So, and we know about the solubility constant for the partial pressure of for carbon dioxide. So if we know the PCO2 from the ABG, or we can calculate the PCO2, then we can get the H2CO3 concentration level. So, and for this bicarbonate buffer system, the pKa for this bicarbonate buffer system is 6.1. So putting everything into this, we get pH is equivalent to pKa of 6.1, which this is fixed, this is constant for this buffer system. Each buffer system has a dissociation constant, pKa. For bicarbonate buffer system, for this equation is 6.0. For something else, it can be 6.8. For something else, it can be 9.2, like amino acid and everything. Since we are talking about the bicarbonate buffer system, which is involved in the Anderson-Hasselbalch equation, we know it is 6.1. So we put in 6.1 here. And then to H2CO3, we're going to put the PCO2 that we're going to measure. So the full equation for this bicarbonate buffer system is pH is equivalent to 6.1 plus log 10 bicarbonate concentration divided by 0.03 times PCO2. Okay. So going back to this is the full summary of it. How do we get each of it? pKa is the acid dissociation constant of carbonic acid, which is 6.1. Bicarbonate, concentration of serum bicarbonate. H2CO3, concentration of carbonic acid, which cannot be get directly, but we can use the Henry's law using partial pressure of carbon dioxide and solubility constant to find the carbonic acid concentration, and then we substitute it into it, and then we get this full equation. Okay. Next. Again, we are coming here. This is just a repetition of all these things. Let's say you don't know the pH. Let's say you are ABG. We just take it as our ABG doesn't give us the pH now. Okay, just take it, your ABG mission, the pH region is not working, it doesn't come up, but you got the PCO2 and bicarb value, and you know the pKa is 6.1. Can we calculate the pH? Yes, of course, using this formula. So pH is 6.1 times log to the power of log 10 of bicarb over 0.03 times PCO2, and we know this value. You just substitute this value. Okay, the bicarb is 24, and 0.03 times 40 is 20. Okay, if this is a normal LP in a normal person pH, it's like a neutral pH. So you get 6.1 plus log 20 is 1.3. So 6.1, 1.3, this is why you get your pH of 7.4. pH of blood plasma is 6.1 plus log serum bicarb or serum carbonic acid, which you get 6.1 plus log 20, which this, and then you get 6.1, 1.374. That's how we get the neutral pH of a normal ABG. I hope you all understand this. Okay, let's see how does it differ we talked about this in a normal ABG. We just say in metabolic acidosis what happened. So in metabolic acidosis, let's say the PCO2 is normal, still 40, your respiratory compensation doesn't work place yet. Your PCO2, if the patient is not hyperventilating, the PCO2 is still maintaining at 40, but the bicarb level has dropped to 17. So if you consider 6.1 plus log 10, 17 divided by this, you get log 14, you get 7.25. This pH is low because your bicarb level is low and there is no respiratory compensation. If there is respiratory compensation and this PCO2 has been brought down, then this pH would have been higher. Okay, let's do a simple clinical work here. Just get a piece of paper and go along with me, so at least you all understand this better before we go into the discussion. Okay, you are ventilating a patient with tidal volume of 600 ml and a respiratory rate of 10 per minute. let's say this patient is admitted with pneumonia and HAI lah. Okay, it's a pneumonia. So you have 600 ml, your ventilator setting is 600 ml and respiratory 10. So you get a minute volume of 6 liter per minute. And you took an ABG, the ABG showed PaCO2 of 55 millimeter mercury, pH of 7.30, bicarbonate is 26. The patient is somewhat having renal compensation already. Okay, it's a bicarb at the higher normal level. You want to aim a pH of 7.35 for this patient. So what should you do to reach the pH of 7.35? Of course, at this point, you all will know we have to hyperventilate, doctor, because the renal compensation is quite okay. So we have to hyperventilate because the PCO2 is high. So what is the PCO2 that you have to achieve? You have to brought down until you can reach the pH of 7.35. So the question is, what is the required PaCO2 to achieve pH 7.35? And to achieve the PaCO2 that we have calculated here, what is the alteration in the ventilator setting that we have to do to achieve that? Okay, first, step 1, we find the expected PaCO2. We know this formula already. Okay, we're going to use this formula. So you're going to put in 26 bicarb here. Okay, and you're going to put in, if you put in bicarb of 26 here and the PCO2 of 55 here, you will get a pH of 7.3. Okay, but we want to find expected PCO2, so we want to put pH of 7.35 here. So we can find what is the PCO2 we want to find. We want to find the PCO2, so we know we want to aim 7.35, and we know the bicarb currently is 26. So what is the PCO2 that we have to achieve to reach the pH of 7.3? So we rearrange the equation. So you put the equation first. 7.35 is equivalent to 6.1 log 10, 26 is the bicarb, and this is the formula. Okay, then bring down the 6.1 here, 7.35 minus 6.1, you get 1.25, equivalent to log 10, 26 by 0.03 of PCO2. And you anti-log it. This log, it comes in, it becomes anti-log. Here, but you want to find the PCO2, so you want to bring everything over this side. So log, we come here, anti-log 1.25, equivalent to 26 divided by 0.03 PCO2. Then you bring the PCO2 here, anti-log goes there, 26 divided by 0.03 times anti-log 1.25. And then 26 divided by 0.53, you get a value of 49 millimeter mercury. I didn't complete this equation here. The answer is, I think, 49 millimeter mercury. Please check and see whether you all got the answer, same answer like what I got or not. 26 divided by 0.53. Yes, 49 millimeter mercury. So the answer will be 49 millimeter mercury. To achieve the pH of 7.35, you have to achieve partial pressure carbon dioxide of 49 millimeter mercury. Okay, this is the first part of the question. So how do we gonna achieve the partial pressure of 49? From 15.5, you have to drop it to 49. So how do we gonna do that? Okay, so what is the change in the patient's VT is required to achieve? You have to use the alveolar ventilation equation to find the target minute volume to achieve this PCO2. I am not going to talk about the full lengthy part on the alveolar ventilation equation. As I said, this is just for clinical part. You have to use the alveolar ventilation equation. This is the alveolar ventilation equation. If you rearrange the derivation and rearrange the equation and derive it, you will get the alveolar ventilation and partial pressure carbon dioxide known times equivalent to ventilation, alveolar ventilation times the partial pressure carbon dioxide desired. Okay, we know currently the PCO2 that we have is 55, and then we want 49 millimeter mercury. We already know we are ventilating with minute ventilation of 6 liter now. We want to find out what is the ventilation that we have to achieve to get the 49 millimeter mercury. So you rearrange it, 6 times 55 divided by 49, you get 6.73 liter per minute. It means you have to increase your minute ventilation from 6 liter to 6.73 liter, so you can achieve a PCO2 of 49 millimeter mercury, which will give you a pH of 7.35. So to achieve it, you know, you can either increase the tidal volume or you can increase the respiratory rate. So either you increases the tidal volume from 600 mil to 670 mil to get 6.7, or you increases your respiratory rate from 600 to respiratory from 10 to 11 or 12 to get more than 6.6 or 6.7 liter per minute. Okay, this is just for simple calculation to make you all understand, and you all can practice it at your day-to-day bedside. as well to understand this better. Okay. Okay. That's all about the tutorial. So we're going to go into the question. I'm going to talk about the buffer question first, then we go into the other two questions. Again, during this SAQ, some of the answers may be lengthy, but I will tell you what is needed for exam point of view and what is the lengthy discussion part of it, okay, for better understanding. Again, best answer versus practical answer. I will tell you which part of my answers are practical, which is the more lengthy descriptive answers that I'm going to give. Okay, first he's talking about buffer. So the questions usually start with definition, define buffer, then describe the buffering systems in the body and list the factors that affecting the buffering capacity of hemoglobin. So this goes back to this, the early part of it when I mentioned acid-base buffer system in the body. The main acid-base buffer system is what is the bicarbonate, which is in the plasma. Next, we're talking about respiratory, then we're talking about renal. Of course, the buffer system in the blood, they got a lot of other buffers and then bicarb as well. Okay, so we go to the question per se. First, definition. Okay, this is the examiner report, okay, for this question from NS. So you see, they say many candidates confused and answered according to the response toward acidosis. Okay, buffer, respiratory compulsion, kidney correction. Here, but they ask as in general. They didn't mention the pathology here. They didn't mention acid-base imbalance, but they are asking you to talk in general about buffer. So here they say the buffering system can be divided into extracellular and intracellular. Okay, there is many ways to divide buffer, but here they more went into this approach and they talk about the factors affecting hemoglobin. So we don't have to go through this. I will discuss whatever their examiner report in my answer. So define buffer. You have to know this definition by heart. It is a solution which has the ability to minimize changes in pH. Okay, it is a solution which has the ability to minimize changes in pH. Or you can say it's a solution which has the ability to resist the changes in pH, whatever lah. When an acid or base is added to it, this is a complete definition. If you stop at here, it does not complete. It means you have a solution and you're adding acid or base into it. Of course, there will be some changes to the concentration of hydrogen or hydroxyl ion to it, which is going to make a change in pH. But if that solution has buffer in it, it can minimize or it can resist the changes in pH when an extra acid or base is added to it. Okay, that is what is meant by buffer. And if the mark is 1 mark, if you just stop at this, you might not get the 1 mark. So you have to add on a bit. It binds, a buffer binds hydrogen ion reversibly to minimize change in pH. How does it minimize change? You just have to add this general equation. No need to mention what type of buffer. Buffer plus H plus is H dot buffer. Buffer consists of a weak acid or conjugate base. A buffer solution consists of a weak acid or conjugate base. This is a complete definition, which sure you can get 1 mark. Okay. If you want to add on, you can say it can be divided into intracellular or extracellular buffer, or another classification is open bicarbonate or closed non-bicarbonate system, which is a more practical one. Okay. This is the physiological one, but this is the more practical one. Open bicarbonate or closed non-bicarbonate buffer. As I mentioned, bicarbonate buffer is the most abundant buffer system in the body. It's open because open means it is the carbonic acid equation. The carbon dioxide can be eliminated to the environment. That is the open part they are talking about. Whereas the closed non-bicarbonate system, which is all within the body in vivo, it is not in relation with the atmosphere. Okay. So this is the way. So you see, bicarbonate acid system, it's an open system. It is to acid buffer is fixed, non-volatile and volatile, whereas non-bicarbonate is for volatile and fixed acid. It can, non-bicarbonate system can use for both, whereas bicarbonate system is mainly for volatile. I'll come into it. Okay, I'll come into it. So the practical classification of open bicarbonate system is either plasma bicarb or RBC bicarb. Okay, the bicarbonate system can present outside the RBC or in the RBC. Okay, whereas closed non-bicarbonate system, we are talking about hemoglobin. Hemoglobin has buffering capacity using bicarb system and also non-bicarb system, organic or inorganic phosphate, and we have plasma proteins as well. Okay. First, we're going to talk about bicarbonate, non-bicarbonate buffer. Okay, this is the tutorial parts of it. We haven't gone into the answer of the SAQ yet. We answered the first question. Okay, we haven't gone into the second part yet. Before that, I'm going to explain about bicarbonate, non-bicarbonate buffer. Bicarbonate buffer system consists of H2CO3 and conjugate base bicarb. This is the one we talked earlier, the equation. Non-bicarbonate buffer system consists mainly of phosphate, organic and inorganic, and proteins, including hemoglobin. Hemoglobin is a protein. Okay. The blood buffer base is the sum of the bicarbonate and non-bicarbonate buffer. The whole buffer system that ever, it is a combination of these two. Okay. And then the bicarbonate buffer system is called an open buffer system because H2CO3 is an equilibrium with dissolved CO2, which is readily removed by ventilation. As I mentioned, we can be exhaled to atmosphere. That is, when H plus buffered by bicarb, the product is H2CO3 broken down to H2 and CO2 as long as the ventilation removes CO2. We have talked about this, the same thing. This thing goes to here and H2CO2, CO2 exhale. The removal of CO2 from the reaction prevents it reaching from equilibrium reaction. Because this CO2 is continuously being eliminated, so this reaction can go in this direction. Okay, so it doesn't reach equilibrium unless the CO2 elimination is stopped. Okay, that is why if the patient stops breathing, this CO2 cannot be eliminated, so this reaction will go here and H plus will increase, causing acidosis. Okay, non-bicarbonate buffer system is called as a closed buffer system because all components of acid-base reaction remains in the system in vivo. Okay, and when H plus is buffered by buffer, the product H buff, this equation, so the buffer can be in non-bicarbonate system, it can be anything. This buff can be protein or phosphate, hemoglobin or whatever, accumulate and eventually reaches equilibrium with the reactant, preventing further buffering activity. You see, that's the difference between non-bicarbonate and bicarbonate. Bicarbonate can go continuously without reaching equilibrium as long the CO2 is continuously being expelled, whereas non-bicarbonate buffer will come to a halt at certain point. So buffer plus H buff. When this H buff already reaches this equilibrium, this all three, then it will stop. It won't continue because this one cannot be eliminated 100%. Okay, open and closed buffer system, they have different roles in buffering fixed and volatile acid. Please pay attention here. Body carbon dioxide production, elimination via ventilation, H2CO3 accumulate. Okay, this is how we do it. If the body's CO2 production is more than the elimination of CO2 via ventilation, more CO2 being produced, but patient is hypoventilating, means less CO2 expelled, the H2CO3 will accumulate. The reaction between CO2 and H2 move continuously towards right, more H2CO3 and more H plus and bicarb. This is why we get respiratory acidosis. The bicarb produced in this way incapable of buffering H plus, which is because why I'm talking about this here, you may ask me, since this reaction can go back and forth, so if the patient is hypoventilating, CO2 accumulates, become carbonic acid, H plus. Why can't this bicarbonate produced in this reaction just buffer this H plus directly and cause this reaction to be not H plus to be high and cause acidosis? Cannot. The buffer system cannot buffer their own byproduct. The H plus is byproduct of this buffer system, this bicarbonate buffer system, and the bicarbonate is produced in this reaction cannot self-buffer the H plus that is produced. Okay, the bicarb produced in this way is incapable of buffering the H plus which is co-produced. So to buffer this H plus which produced secondary to respiratory pathology, we have to have non-bicarbonate buffer system. So the only buffer system that can buffer the H plus of volatile acid, okay, is the non-bicarbonate buffer system. That is the importance we have bicarbonate and non-bicarbonate buffer system, because the bicarbonate buffer system cannot self-buffer the hydrogen ion produced in the reaction. So both non-bicarbonate and bicarbonate buffer system can buffer the H plus produced by fixed acid. Okay, bicarbonate buffer system only can buffer the fixed or metabolic acid. They cannot buffer the carbonic acid. But non-bicarbonate buffer system can buffer volatile and non-volatile acids. This is what we are talking about. Okay. Both non-bicarbonate and bicarbonate buffer system can buffer the H plus produced by the fixed acids. Okay. True for bicarbonate buffer system only if ventilation is not impaired. Again, as long the CO2 is being eliminated, then this bicarbonate system can work. That is the rule. Okay. Again, fixed acids can be buffered by both bicarbonate and non-bicarbonate buffer system, but volatile acids only can be buffered by the non-bicarbonate buffer system. Okay, please understand this part. Both systems are physiologically important, essential role in maintaining pH homeostasis. So this is the lengthy part of explaining how does the bicarbonate and non-bicarbonate buffer system works. So look at it. So I told you bicarbonate buffer system is an open system because CO2 removed by the ventilation. This is the bicarb from the body store. So if there is a H+, this H+ cannot be self-buffer. It by added fixed acid, it goes to here, it's buffered by the non-bicarbonate buffer system. But the H+ from the fixed metabolic acids can come here and can be buffered both sides. The added fixed acid can be buffered both sides. So again, this is again the blood H+ goes here, can be eliminated. The fixed acid H+ can go to bicarbonate buffer system and can be eliminated. And the H+ from the fixed acid can be buffered by both sides as well. Both buffer systems intermingle in same solution, whole blood, in equilibrium with the same H+. Increased ventilation increases CO2 removal rate. Non-bicarbonate buffer H+ to release H+. This part, CO2 goes away, the H+ comes here, can be released. Decreased ventilation ultimately causes the protein buffer or other buffer to accept more H+. When this reaction doesn't go, and the reaction will go this way. If this reaction, the carbon dioxide ventilation is unimpaired, is working fine, it always favors this way because this is fast. But let's say this is altered because of certain pathology, some respiratory issue, then it will go this way. Okay, next we comes to the question per se. So describe the buffering system in the body, 6 marks. The question describe and it's 6 marks. So of course, I will start off by drawing this. Okay, you can talk about the open system and closed system. If I'm answering the question, I would have divided in open and closed system, which is more practical, but the examiner report was talking about extracellular and intracellular approach. But if you have answered via open and closed also, you won't be penalized because the core of the answer finally is the same. It's just the way of dividing it. I would have answered it in this way. It is much more easier to explain. Okay, open bicarbonate also. So we will go along with the, we have talked about this open and non-open, open and closed approach. So now I will go along with the examiner report. How do they answer? Extracellular and intracellular. Extracellular is blood bicarbonate or CO2 system, plasma protein and minor system, CSF, with carbon dioxide, calcium carbonate in bone, phosphoammonium in system in kidney and everything. Intracellular, a protein and phosphate. Again, this hemoglobin RBC bicarbonate system, some books mention as extracellular. They merge it along with this blood, but it is ideally should be intracellular because it's happening inside the RBC. RBC is a cell. But if you put it here along with the blood also, you won't be penalized because many books actually mention it as extracellular. Okay, about blood bicarbonate system, you have to mention this equation. You can start off with this equation. About the blood bicarbonate system is the most abundant buffer system in the body. It defines the body pH. It has a pK of 6.1. It is an open system. It's a very effective. CO2 is regulated by the pulmonary system or respiratory system, while bicarb is regulated by the renal system, the body store. Can only buffer metabolic acids, not carbonic acid. This is a key point. As in, again, I'm saying it cannot self-buffer the hydrogen ion produced in this reaction, can only buffer metabolic acid. You have to mention at least this much point to get good 2 marks or 2.5 marks from here itself. Okay, in this answer, 6 marks, majority of the marks go to this bicarbonate buffer system. They want you to talk about this. They want you to understand this part. Okay. Again, repetition. What happens when there is fixed acid? It will be buffered by this system. CO2 is being eliminated. When patient hypoventilate, the CO2 accumulate. This reaction will not move this way, and it will go this way. So this, you want to mention this or in equation, or you kind of mention in words as I mentioned earlier also can, but minimum, the practical answer is this part, the upper part. You have to mention this. Next, extracellular, the number one is plasma protein. You have to give few examples, albumin and globulin. How do they buffer? Because side chains of all these proteins can buffer the hydrogen ion. The side chains can be amino, can be carboxyl or imidazole. Each of them of certain pKa, pKa 9, pKa 2, pKa 6.8. These are closed system. These are not open system. Plasma proteins are closed system. When you have closed system, there is a concept you have to understand. If their pKa is too far from the neutral pH or the cellular pH, it doesn't work well. It has to be closer to the pH of the solution that being added. The buffer, if the pKa is nearer to the solution pH, it works fine. So the imidazole of the hemoglobin 6.8, the intracellular pH is usually 7. What? Slightly acidotic. It is not 7. So this is the best one. These are all not so effective. Again, plasma protein in extracellular, these are, we are talking about plasma protein, not proteins as in cellular. Plasma protein means extracellular. They are not inside the cell. They are not very significant in ECF because plasma protein concentration is comparatively lower than the concentration of protein in the intracellular fluid. Okay. So again, this equation you have to write. For plasma protein extracellular, you write minimum this much. If you don't remember this exact pKa, also no problem. Next, we go to intracellular. You have to mention about these three. You have to at least have to say intracellular buffer consists of proteins, phosphate, and hemoglobin. For protein, you're going to write this simple equation. We're going to mention more buffering capacity in ICF due to proteins higher in concentration. More acidic environment, improve buffering quality. This part lah. Why proteins in extracellular? Because concentration is lower, whereas in intracellular, it is more. Okay, you write this much is more than enough. For phosphate, you're going to mention this equation, H plus HPO4 2 minus become H2PO4 minus. It can be organic or inorganic. You have to mention the pKa of phosphate is 6.8, which is nearer to the intracellular pH of 7.1. So it is a very effective buffer because this total concentration of phosphate is high in intracellular and intracellular fluid pH is lower, which is 7.1, nearer to pKa. You should be able to remember and say this much. You have to able to say the concentration high, the pH is lower. For again, repetition for closed system, if the pKa is nearer to the pH, it will work better. Next, hemoglobin, you're going to mention H plus hemoglobin is HHB. You don't have to write the full one. You write this much. The simplified buffer equation is more than enough. You have to mention it is the major buffer for volatile carbonic acid. Okay, it is the major buffer for volatile carbonic acid. Again, the pKa is 6.8. The side chain is imidazole, if you can remember, which has the histidine amino acid residue. If you can remember this, well and good. But if you can mention the pKa 6.8, also good. How does that hemoglobin do this buffering activity apart from the bicarbonate system? Hemoglobin, remember, it has multiple way of buffer. One is directly the deoxyhemoglobin directly buffering the HB, and by forming a carbamino formation, also by aldane effect. This is the aldane effect, the deoxyhemoglobin directly buffering. So if you can mention it is a major buffer for volatile carbonic acid, 1 point. You can mention about this equation, second. You can talk about the pKa, and if you don't remember this full equation of carbamino, you can just mention keyword. The buffering is done via aldane effect, and carbamino formation is more than enough. Okay, so this is the what is happening within your erythrocyte. So it has three different phenomena. One is the bicarbonate buffer system. One is the deoxyhemoglobin buffer system. Another one is the carbamino formation. Okay, here if you read Kerry Brandis, they'll talk about the hamburger effect of chloride shift. This is to maintain the electroneutrality. The bicarb will be constantly brought out from the cell, so this reaction can go further forth. So to maintain the electroneutrality, the anion is going out, the chloride will come in. That is the hamburger effect of chloride shift, to maintain the electrical neutrality, but the concentration of bicarb will be brought out to maintain low concentration. So this reaction can go continuously, can go and forth. And then deoxyhemoglobin also can combine. Carbamino formation, I'm not showing here, in the next slide. Okay, this is for answer to the FAQ. As I mentioned, this is extra information. How does carbon dioxide transport and buffering is can be understand together. Please go and read Kerry Brandeis together about the page 24 to 31 about buffer and acid-base balance, and flip the page, go back to respiratory section and read the carbon dioxide transport also today, so you understand it together. So again, so carbon dioxide transport in your blood is happening via 3 ways. 5% is happening via dissolved in plasma, carbon dioxide being dissolved in plasma. 90% is carried by the RBC hemoglobin, another 5% via the carbamino formation. Okay, so there are 3 ways. One is dissolved plasma, which is 5%. Another 2 ways is within the RBC. One is catalyzed by the carbonic anhydrase, which is involving the Bohr effect, 90% of it. Another 5% is minimally via the carbamino hemoglobin. Okay, first, we go one by one. We don't talk about this dissolved plasma. It is direct, dissolved, use the carbonic acid reaction is bind to plasma protein. Okay, I put the numbers here 1, 2, 3, 4, but in real it doesn't follow the sequence. It happens simultaneously, just for understanding. Okay, imagine this is the tissue cell. The carbon dioxide from the tissue, it dissolves and it transfers the membrane and goes into the RBC. First, we talk about the carbamino hemoglobin. Carbon dioxide combined with the hemoglobin forms carbamino hemoglobin. This one, the full form of it. Okay, the amino compound of it. Hemoglobin as the amino acid component, which is the histidine residue of amino acid, HbNH2 plus CO2, you get HbNHCO minus plus the H plus. So it liberates H plus here. Okay, so this reaction also liberates H plus. Next, Bohr effect. Carbon dioxide goes in, carbon dioxide plus H2O is catalyzed by the carbonic anhydrase, H2CO3 minus, produce bicarb and H plus. Bicarb is constantly removed by the chloride shift and Hamburger to maintain electronegativity. Again, H plus is liberated. So this H plus. Okay, next we have aldane effect. The RBC that reaches the cell is the hemoglobin is fully saturated hemoglobin. So this CO2 loading gonna cause the unloading of oxygen. That is Bohr effect. Bohr effect says CO2 loading, oxygen unloading. So since the CO2 is loading here and liberating H plus, this H plus all cause this Bohr effect, causing oxyhemoglobin to release oxygen, and the hemoglobin become deoxyhemoglobin. And the oxygen that is released will be pushed to cell. And oxygen unloading again will favor the CO2 loading. So aldane effect. Aldane effect is oxygen unloading favors more CO2 loading, and the CO2 loading will cause this buffering effect again. So the H plus that liberated from this bicarbonate, this carbonic acid reaction and this carbamino hemoglobin will combine with deoxyhemoglobin. This deoxyhemoglobin will combine with this become buffered deoxyhemoglobin. And this buffered deoxyhemoglobin will brought to the lungs, and then it will be eliminated via this bicarbonate. It will again broken down, since when it reaches the lung, this HHB, buffered deoxyhemoglobin, will release oxygen and H plus will release. And this reaction will go this way and CO2 will be released in the lung. Hope this you all understand. So Bohr effect, CO2 loading, oxygen unloading. And oxygen unloading, aldane effect, more CO2 comes in. The H plus that is produced is via this carbonic acid reaction and also carbamino hemoglobin will be buffered by the deoxyhemoglobin. That's why the oxygenation state of the hemoglobin is important. Deoxyhemoglobin has a higher buffering capacity compared to oxyhemoglobin. Okay, hope this is understandable. Again, I took this picture from Kerry Brandeis. It is a more simplified manner. This is in picture and animation and everything. In exam, if you can write this and explain, this is the perfect. This is talking about carbon dioxide transport and gas exchange in red cells, and also talking about the buffering. The same thing, you can see plasma CO2 dissolve goes in Bohr, CO2 loading, and then you're talking about 5% of carbamino hemoglobin. They're not talking about the dissolved 5% here. So dissolve, then 95. Again, the H plus comes here, H plus comes here. The H plus is buffered by the deoxyhemoglobin, and deoxyhemoglobin, if oxygen is unloading, causes the aldane effect. Okay, you can look into your Kerry Brandeis. Okay, next we go into the next question. This is the straightforward question saying list the factors affecting the buffering capacity. List. It's already given you the keyword list. So you're only going to list 3 factors. By mentioning only 3 factors, can you get 3 marks? No. You have to slightly give an explanation to it. So first, the 3 factors that affect the buffering capacity of hemoglobin is the pH of the solution, state of oxygenation of hemoglobin, and hemoglobin concentration. The pH of the solution, the closed buffer are only effective at pKa 6.8 plus minus 1. This I said when the pKa is nearer to the intracellular pH of the solution, it works better. State of oxygenation hemoglobin, deoxyhemoglobin is better buffer due to aldane effect. You just have to mention this keyword is more than enough. Hemoglobin concentration 2 times more than plasma protein. The hemoglobin concentration in your body is double the concentration of plasma protein, and since they are double, each hemoglobin has this imidazole group with histidine amino acid residues, which gives the pKa of 6.8. So all these are the factors that affects the buffering capacity of hemoglobin. So if the patient has the pH of the solution is nearer to the pKa, is better. If you have more deoxyhemoglobin, they can better buffer. If the hemoglobin concentration is higher, they can be a better buffer. Okay. Next, we go to acidosis. We talked about acidosis versus alkalosis. So the definition, you can at least have to say a bit more. You cannot simply say it's lower pH alone. So respiratory acidosis, high CO2, metabolic acidosis, low bicarb. List the causes of metabolic acidosis. I'm sure you all are very well versed with it. When you talk about metabolic acidosis, you cannot simply say the causes. You have to divide it into normal and high anion gap. I'm not going to go into the depth of it. There is a multiple way of remembering it. The famous one for high anion gap is mud piles. For normal anion gap, there is a few things like Durham, hard ass, whatever. So keep you remember one and stick to it so you can understand. It is a 3-mark question. So I think you at least have to mention 3 untuk normal, 3 untuk high anion gap lah minimum. Okay, you can't only say high anion gap. As an anesthesia master student, we will expect you to divide it into normal and high anion gap. Okay. Next, we go to the question which is the bulk of it. Describe the renal response to a metabolic acidosis that would occur in a normally functioning kidney. 6 marks. Again, renal physiology is a lot of people stumble upon. So they already give you a specific pathology here, metabolic acidosis, and they already say this kidney is functioning normal. So a practical answer should at least be able to mention what are the process, how do they correct this metabolic acidosis, the kidneys, how do they gonna respond to the metabolic acidosis, and what are the steps or process involved. So you should be able to at least mention kidney response to metabolic acidosis by increases the reabsorption of bicarb and increases the net excretion of H+ as titratable acid. Okay, why I'm not putting full form here? Because I already used full form. In your exam, please put a bracket here for bicarb, for the bracket here for hydrogen ion. After that, you can just use this short form or this symbol. At least once you have to put a full form. Increase the reabsorption of bicarb, increase. This is the only way of excreting fixed acids. Okay, so again, you see this is the only way of excreting fixed acids. The process involved are secretion of H+ in proximal tubule. So secretion of H+ in proximal tubule, which accounts for the reabsorption of 90% of filtered bicarb. Secretion of H+ into distal tubule, H+ mostly buffered by the phosphate buffer here. Also, some bicarb reabsorption occurs here. And the third process is secretion of ammonium NH4+ into proximal and distal tubules. This is the practical answer, which is you should be at least able to write this. And you can get minimum 3 or 4 out of 6 marks, as I can tell you. At least 3 marks lah, because all the keywords are there. At least if you can say this. Okay, because all the keywords are there, you have tell them how they respond and you have mentioned the process. Okay, now we go into the full 6 marks answer. How do we gonna? So we're gonna have to explain this process for you to get the full 6 marks. So we are talking about bicarbonate reabsorption. We are talking about hydrogen ion excretion. We are talking about ammonia genesis. These are the 3 processes that involved in the renal response to metabolic acidosis. So the bicarbonate reabsorption, The kidney increases the reabsorption of bicarbonate up to 90% in the proximal tubule. It buffers the excess hydrogen ions in the blood, reducing acidosis. The reabsorption of bicarb, excess bicarb reabsorbed, can go and combine with H+ to produce carbonic acid, and the carbonic acid can be broken down to CO2 and H2O and can be eliminated. If you want, you can put down that equation there as well. So this is what happens here. So this is your lumen, this is your blood. So bicarb is being the CO2 plus H2O, H+ plus bicarb. The H+ is being eliminated and bicarb is being reabsorbed along with your sodium. And this is the reabsorption of bicarb. The CO2 plus H2O again, H+. Yeah. Okay. So this is the back and forth reaction that is happening. If you want, you can mention here. You can write this, is well and good. Next, increase hydrogen ion secretion. The kidney increases the secretion of hydrogen ion into tubular fluid, primarily in distal tubule and collecting duct. In PCT, it mostly bicarb reabsorption, where hydrogen ion secretion, it also occurs in PCT as well, but it mainly occurring in the distal tubule and collecting duct. The secreted H+ combined with urinary buffers like phosphate, ammonia to form titratable acid like H2PO4-. This is why I mentioned H+ combined with HPO4-2- will form H2PO-, and NH3 ammonia combined with H+ will form NH4+, which are then excreted in the urine. These are the equations that we talked about just now. Next, ammonia genesis. What is ammonia genesis? Is production of ammonia from glutamine in the proximal tubule. So glutamine is again amino acid buffer. So increase the production of NH3 from glutamine in proximal tubule. Ammonia acts as a buffer. Once the ammonia is produced, this ammonia acts as a buffer. This reaction will happen. Ammonia combined with H+ to produce NH4+, excreted. This goes here. Okay. So ammonia that is already in the body, and the kidney also producing more ammonia using the glutamine in proximal tubule to go back to this reaction. So this is what we are talking about. Glutamine can produce 2NH4+ to bicarb. The bicarb will be reabsorbed and its oxaloglutarate will be eliminated from the urine. This is the lengthy part of it. Okay, if you can remember and write this is okay. But otherwise, if you can put these in words, you will get 6 marks for sure. Okay. Another concept in renal, in acid-base balance, is about the proximal convoluted tubule being high capacity, low gradient, and distal convoluted tubule being in low capacity, high gradient. This is a very good concept to understand. I want you all to go and read Kerry Brandis. They've explained it wonderfully. Okay, please go and read. Okay, next we're coming into the final question. Discuss the role of following organs in acid-base balance. Again, they never give you any pathology. They didn't tell you it's acidosis or alkalosis. They just want you to talk about these 3 organs in acid-base balance. A lot of answer has been discussed. It's going to be overlapping. So the major organ that involved in acid-base balance is lung and kidney, but do not forget about liver. Liver also has an important role in acid-base. So we're going to talk about it. Again, this is the examiner report. They said many of you confused, and many of the candidates before they confused and wrote about CO2 transport rather than the CO2 as involved with the Henderson-Hasselbalch equation and the bicarbonate buffer system. Okay, and you have to mention about lung being a rapid response but incomplete, but kidney is a slow response but more complete, and finally role of liver as well. Okay, so acid-base regulation by lung and kidney is the main one. We have talked about it. The CO2 is eliminated by the lung, is a large capacity, whereas kidney is mainly important for other buffers, and it's a non-volatile acids are eliminated by the kidney with the regulation of bicarb. Okay, this is the minimum you have to write to get at least 4 marks. Okay, out of 6 marks. This is without explanation, at least 3 marks lah. Okay, this is a 10-mark question. Sorry, it's a 10-mark question. Out of it, if you write this key point, I think you can at least get 5 marks. A passing mark, you are talking about what is happening. If you're not able to explain fully, or if you can explain a little bit here and there, you can get a 5 or 6 easily. But these are the key points. So when you talk about lung, you're going to talk about the CO2 exhalation bicarbonate system we had talked about earlier. And how does this respiratory compensation occur in a pathology using a chemoreceptor regulation. And kidney, we talked about the 3 processes, the reabsorption of bicarb, next excretion of hydrogen ion as titratable acids and ammonogenesis. And liver, They have 4 important roles. Liver is a very highly metabolic organ, so they have a lot of metabolism goes on, and carbon dioxide is byproduct of all that metabolism, especially oxidative metabolism. So a lot of carbon dioxide produced is contributing the carbon dioxide store in your body, which is can be a carbonic acid and become hydrogen ion as well. And then metabolic of organic acid ions. The liver is involved in lactate metabolism. They get involved in a lot of amino acid metabolism and ketones metabolism, which can be involved in the contribution to the store of fixed acid, and also it can reduce the hydrogen ion by metabolizing lactate to glucose in gluconeogenesis as well. And metabolism of ammonium in urea cycle will come into it. And don't forget, it is also liver is a synthesis place for plasma protein, especially albumin. It can act as a buffers as well. So in a detailed answer to get full mark, you're going to talk about lung rapid response. The lung response in acid-base balance is within minutes, but incomplete. Buffering by elimination of CO2, which is volatile acid, very high capacity. Okay, because the questions are role of organelle in acid-base balance, means how do they act as a buffer, or what do they do in acid-base balance? So the lung is mainly with a very high capacity or very important role in acid-base balance. What do they do? CO2 exhalation, and during CO2 respiration, the respiratory compensation come into picture. So you're going to write this equation again. Lungs excrete CO2, a byproduct of cellular metabolism. CO2 combines with water again. If you already write this equation, you don't have to put into words. By exhaling CO2, the lungs reduce the amount of H2CO3, decreasing the acidity, or vice versa. Let's say if it's alkalosis, we are talking about other ways now. Okay, how do they do it? We have chemoreceptors, peripheral and central chemoreceptors. For regulation of your respiration, the main bulk comes from your central chemoreceptor, but the central chemoreceptors are slow. Peripheral chemoreceptor only account for 20%, but their action is, the response is quick. So peripheral chemoreceptor only account for 20%, but they are quick, which is related in carotid bodies and aortic arch, and central chemoreceptors in medulla account for 80%, but comparatively slower in the medulla, detect changes in the pH and CO2 levels. Acidosis stimulate peripheral chemoreceptors, increases the minute ventilation, reduce the PaCO2, and reduce the bicarb because it goes this way. Okay, so CO2 comes down, H plus goes this way, then H plus comes down. From Anderson-Hasselbalch equation, this is how you're relating to Anderson-Hasselbalch equation. So you write this Anderson-Hasselbalch equation, you can say PCO2 drop, the pH will improve. Okay. Next, kidney. I'm not going to go into it. We just discussed it. We're just going to add on few introductory points for kidney. It has a slower response in acid-base balance compared to lung, hours to days, but it finally gives you a complete compensation. It is buffering the fixed or metabolic acid. It has a low capacity of acid-base response compared to lungs. Again, bicarbonate absorption, hydrogen ion excretion, ammoniogenesis. We are not repeating this. Is the same answer as we just discussed. And liver contribute to acid-base balance through various metabolic processes that I mentioned. So urea cycle. So these are the four components of liver, how they contribute to acid-base balance. First is urea cycle. The liver converts ammonia, NH3, a byproduct of metabolism, into urea. Ammonia is converted to urea, which is less toxic and excreted by the kidney. So it doesn't contribute to the body's hydrogen ion store. This process consumes bicarbonate, influencing acid-base balance as well. So this ammonia to urea consume bicarbonate, so it reduces the bicarbonate level in the body, so influencing acid-base balance. Lactate and ketone metabolism. Liver metabolizes the lactate, which is produced during anaerobic respiration in hypoxia time, into glucose via glucogenesis, so it reduces the lactic acid level. That is why in a patient with liver failure, you have increased lactate because it is unable to metabolize the lactate into glucose. This process helps prevent lactic acidosis. Liver also involved in ketogenesis can add up to the fixed acid store. It increases the acidosis. Protein metabolism, liver has amino acid metabolism, producing bicarbonate and consuming H plus in the process, increases the bicarbonate store, reduces the H plus, and it also produces albumin, other protein synthesis, which acts as a buffer. And finally, as I explained, liver is a highly metabolic organ. It contributes up to 20% of the body CO2 production. So this is about liver. Okay,